And there's the website, Alerts, McMaster, Optimal, optimalaging.org, yeah. It's a great one. And they're not trying to buy your support. They're not getting anything from you from this. I think it's a really good thing for MAC to do. I don't know if UT does it, but if you don't, it should. It's a good thing. It has added value because it reflects the region and what's available here and what's not available. So anyway, it's a great source, so you might keep that in mind. So that's my little sales pitch. Well, showing you just how complex things are in the nervous system. What we're talking about today is signaling, sending messages, sharing messages in the brain, and it's quite extraordinary. This is a cortical cell in the neocortex that projects to nerve cells in the spinal cord, motor nerve cells, and where is it? I had it before, but yeah, because I'll tell you, one of the formative people in my career was Charles Phillips, and Charles Phillips died about a decade and a half ago, and tried to talk me into coming to Oxford and staying permanently and joining him in research. And I was really excited about it because what he was actually a physician, got into research. I don't even think he had a DPhil or a PhD, and he did very well. But what he was interested in were the nerve cells in the motor cortex that control motor nerve cells in the cervical cord and the lomosacral cord that control our hand and forearm and feet and lower legs, and especially those that were directly connected, meaning when this cell fired right there, those cells fired down in the spinal cord. It wasn't a problematic thing. It was very direct. He did a marvelous job. The experiments were long things. I remember, they would go on 36 hours without let up. And they were carried out on baboons, which I wasn't too keen about. But the point is here's the nerve cell body here. Nerve cells in the nervous system have conversations with a hell of a lot of other cells. So these pyramidal neurons are shaped like a pyramid here. There might be as many as 10,000 or more other cells that in some fashion influence this cell through synapses. Now you can bet your bottom dollar those who are talking to this cell far away from the nerve cell don't have a lot of influence. Okay? They're too far away from control center. This is where the action potential is generated. It goes down to the motor nerve cell. So the point is that this huge network, this receiving network here, is talking to a lot of other inputs that influence whether or not it's going to fire or not. Those that project very close to it have a lot of influence. Sounds like politics, doesn't it? Right? And here's an extraordinary one, Purkinje cell. One of the Nobel laureates got a Nobel Prize part for this, but he said, here's the cell body. Imagine how many cells it's talking to, it's listening to. Just look at the complexity of that. It's amazing. So what does signaling mean? Well, and here's an up-to-date kind of science. Here's one of those pyramidal tract neurons. Look at that. Single neuron with over 5,000 axons that are connected to it. So at least 5,000 or more other nerve cells are talking to this cell. and it generates an action potential somewhere in here and sends it somewhere. By the way, this is taken from normal human neocortex. You say, who's going to volunteer for a biopsy like that? Well, the patients are having epilepsy surgery, and it's a tiny little biopsy. But anyway, it's amazing. I'm just kind of boggling a little bit. Well, what about signaling in the nervous system? And I'm very aware of this because of AI these days. It happens to be the silicone kind of variety of this, right? Sending electrical signals, but using silicone processes. And of course, people in AI are, and these last year, the two Nobel Prize winners in proteins and actually in AI in general, always cite that the architecture of the computers are based on the brain, how the brain works. Well, maybe a bit, but not much. I think it's oversold. It's a basic principle in science. In very complex systems, like I tried to overwhelm you with, just showing you a second ago, to begin with a really simple system. The real basics. So if you want to study how signals are formed and are propagated, look at a single nerve fiber. Don't look at 100 or 1,000. It's hopeless trying to figure that out. And that's what Hodgkin and Huxley did. Interesting pair of investigators who are interested in this kind of thing. In the pre-war period, they were at Cambridge University, and it came to the site of Bletchley Park, right? And breaking the code, the German code, and these were biophysicists. And in an era when physics was really big, from 1900 up to about 1950, but they happened to be biophysicists. And so they wanted to understand, okay, what actually happens at a single nerve fiber, one that we can actually see and manipulate. And so, well, here they are. I mean, you know the era when you see black and white pictures. I knew these guys. I mean, I was in Oxford 2 days, and I met all three of them. I was very familiar with their work, with their papers. I was in Toronto. Toronto was a kind of a nowhere those days. It was McGill that had all the attention. Toronto had very good teachers, but not very good science. They had good libraries, and I used them. So I knew these guys, and not so much Hodgkin, well, but certainly Huxley, and I'll refer to him later. John Eccles was an Australian, and came to Oxford in the early 30s. He was very helpful in the later part of my career, or the middle and later part of the career. He saved me a couple of times when I could have really made a fool of myself and something. And in those days, he actually wrote letters and exchanged things. He was a very good mentor that way. I must say, Huxley was the same way with others, not me, but with others. They were very generous. So here are the three that kind of broke it open, but initially Hodgkin and Huxley. And then Bernard Cass, he was the kind of the fourth one in the group. I'll tell you, these four people, their work is elegant, especially Hodgkin and Huxley. If you look at the stuff, if even up-to-date textbooks like coming out this year on neuroscience, they repeat the same figures from Hodgkin and Huxley. And the experimental data sits right on top of the theoretical stuff based on mathematical predictions. And it's gorgeous stuff. Did a very good job. He got out of Germany Jew, got out of Germany in time and moved to the UK, and he knew the other three quite well. This was a small club in those days. We're not talking about a club of 100. We're talking about a club of maybe 10 or 15 that know one another. There weren't that many great setters, and they talked to one another regularly. They saw one another. They corresponded with one another. He was a fantastic teacher. His students loved him, and a great writer. That's hard to be in science, but he was. And then, it's all brought up to date. These Nobel Prizes remind you that time moves on. And 4 years ago, this pair, think about it earlier. They were talking about literally thinking of nerve fibers like the batteries, or an engineering problem. And these guys completely transformed it. Now we had a world in which we knew what the genes were, we knew the cells, we knew the genes that dictated the receptor proteins. So you knew almost everything you needed to know about those cells that they were studying, which were sensory cells for touch, pressure, temperature, and pain. So they were standing on the shoulders of people before them. That's the history of science. Standing on the shoulders of people before, dependable people before, the stuff holds up. So this kind of just repeats what I said. If you want to do that. Well, here's the simple model that Hodgkin went to. They look for the largest nerve fiber they could find. Okay, where did they come from? The squid. Well, here we are. The squid giant axon is almost a millimeter in diameter. You can see it. And that means that you can thread an electrode right up the long length of the fiber without destroying it. Versus try that with a mammalian axon, one of ours, which is 1/400th of that. So that's why the squid axon. It was also a day where there were no research grants. These guys built all their own equipment, including the oscilloscope, everything they had. And in fact, I heard the story one time from Huxley that it was very exasperating at times because, all of that apparatus, every bit of it, was like a chain. And unless all of them were working, the experiment failed. And if it wasn't one thing breaking down, it was another thing breaking down. No wonder the experiments lasted over 24 hours. But they knew precisely what to expect, which is exactly what they got. All it took was all the ducks to actually work in a row. And one night they did. And they just kept going, and they completed their list. And that's the list that won them the Nobel Prize. Now, they weren't thinking about the Nobel Prizes, that kind of thing, furthest from their mind, but it just shows that science can be hard work, and it's not just how bright you are, it's how determined you are, and how focused you are to get stuff right. And that's very, very important. So that's some of the background. Well, now I'm really simplifying everything that they did. Okay, if you stick an electrode into a cell in my hand, like this, stick an electrode into it like that. As soon as you stick it in, and you are kind of registering the voltage drops to minus 80 millivolts. I don't remember the number. But there is a voltage, there's a difference across the memory. That's the first thing. And so there's a zero potential, and it drops to, in this case, minus 80. Then, let's say you inject a little current through that electrode, enough to depolarize it, move it back towards zero. But just an inch at a time. Well, nothing really happens except it does inch back to a certain level. And that level is a threshold. Once you're at that threshold and past, all of a sudden, an action potential takes place, an all or nothing event. It's either going to happen or it isn't going to happen, and when it happens, all of it happens. Right? That is an action potential. That is the basic signal of the nervous system, any kind of nervous system. We're talking about the fundamentals. That's what Klotzman and Huxley were after. Well, then they went further. They said, okay, we understand that. We understand we can produce the all or nothing response and the graded response before that, but why? Why is that happening in nature? And what happens is if you stimulate inject a little current in here, you change the transmembrane potential a little bit right up the threshold, and then you get the action potential. But what's actually happening? At threshold here, there's a great flood of sodium ions that floods into the axon from the outside. That's what drives that big spike. In fact, it's a reversal. It's all the way up to almost close to plus 50 or 60 millivolts. It's a huge swing. Well, what terminates that? An equal and opposite but delayed influx of potassium ions from outside, or at least from inside the cell to outside the axon or cell. That's what they actually apply. So this is the ionic basis, meaning the at threshold when the action potential takes place, you get this enormous kind of flooding of sodium ions into the axon, and then within a fraction of a millisecond, meaning a thousandth of a second, an equal and opposite current, potassium current, moves from inside the axon to the outside. It was beautiful. And he had equations to predict this, and the equations that predicted it, and the actual observation. The dots sit right on top of it. I mean, it's incredible what they did. So I've greatly simplified that, but that's the basis of things. Well, I actually, before I came in here, Phil, you have this too. There's a little skin nerve here, the superficial radial nerve here, and it supplies sensation. I can feel it. Run my thumb right over here, and it'll run into my index finger. There's my superficial radial nerve here. Superficial radial nerve here. Superficial perineal is another one. Remember, the feet are the hands, right? The basic anatomy, we were quadrupeds at one time, so all the nerves and muscles that are right over there are similar, but in a different moves, repurposed. So it has similar nerves. So some of them are myelinated nerve fibers. Okay, this is when the game changes. It changed about 425 million years ago with a jawed fish, meaning the naked axon that Hodgkin and Huxley studied had a cell membrane outside, but it wasn't insulated. Now, cells were acquired that created a kind of a thin sheet of a glycoprotein that had very high resistance and wrapped it around in successive, like toilet paper, around the axon, creating an enormous resistance to any leakage current out through the membrane. So try and stay with me, because that's called a myelinated nerve fiber. We would not be in this room and myelinated nerve fibers not evolved, because it couldn't jam enough nerve fibers and develop a big enough brain to do anything. Okay, so, but imagine in that little thing that I can flip under my finger that's a millimeter, there are 2,000 to 5,000 myelinated nerve fibers and 4,000 to 10,000 unmyelinated. And doesn't that boggle your mind? In a little nerve like that, how many thousands of nerve fibers are jammed into that thing, and how much information is coming. For example, this is a sensory nerve. There are no motor nerve fibers here. But this carries fibers that give, when I touch my finger here, I can touch. And the threshold is low and I can pick it up fairly easily. And the unmyelinated nerve fibers, pain and temperature. Now look at this. Look at the speed. Translated into the legal speed limit of a QEW. The fastest conducting nerve fibers, myelinated nerve fibers, are more than twice the legal limit, 110 kilometers per hour. That's how fast they travel. Right? Unmyelinated nerve fibers are down to 10 kilometers per hour. So they're very much slower. So those squid axons didn't have to transmit their messages nearly as fast. And but to get that requisite speed, and furthermore, I'll show you another. Oh, there's a box. We don't need to see that. Well, here, a good friend of mine, Angelica Hahn, a German-Canadian member of a group that worked with me at one time. This is what a myelinated nerve fiber, a human myelinated nerve fiber looks like from the sural nerve, like the superficial radial nerve coming from the foot. So if it's black, that's the myelin sheath. And you will see as we go along here that there's a little gap here. This is called the internode, this long thing until the next gap, to the next gap, to the next gap, to the next gap. Now I'll tell you that the action potential, the actual action potential, is only generated in these places. Only here and here and here. So the action potential is generated here, refreshed again here, refreshed again here, and here, and here. That's what allows the enormous speed, because it's skipping along the nerve fiber. It doesn't have to kind of conduct the whole distance along here. It doesn't have to do that. It's skipping node to node to node. And here's a common form of disease that we'll talk about, or a group of diseases, demyelinating disease, multiple sclerosis in the nervous system. But there are common ones in the peripheral nervous system. And look at what here. Here's the internode, with more or less normal, not normal, but at least has some kind of myelin sheath. There is absolutely no myelin sheath for here. This impulse is going to die right here. It's not going to be able to jump from there to here. Okay? So that's what happens, for example, with multiple sclerosis. Somebody loses their vision in one eye, which is a very common presentation, and then it recovers in say, a matter of a few days, maybe weeks, with steroids or without anything. Sometimes. These demyelinated segments are remyelinated. Not normal, but enough to restore transmission. Okay? And sometimes the injury to a nerve is so bad that the whole damn thing goes. Not only is the myelin sheath all broken up, but the axon is gone. So for this to recover, this nerve fiber has to regenerate the whole length. How fast does it regenerate? About 1 millimeter a day. So if you severely injure a nerve, say at the root of your neck, it's going to take you a year, or nearly a year, under ideal conditions, for that nerve fiber to actually get to your hand or leg. That's how slow the regeneration is, under ideal conditions. So if you're treating something, best to try and prevent that degeneration of nerve fibers. It's why, for example, some strokes do really badly. If they're severe enough to destroy enough nerve fibers so all of this happens, it isn't going to happen. That person person to watch. And it's just too complicated, too far. And to use an analogy, a bridge too far. So there we are. Now, here's what those things, electron microscopy came along when I was a resident and that kind of thing. It's all very beautiful. Didn't add a lot of information, but that's what they look like. You see, you can't see it from where you are, but I can. This myelin sheath is just full of layers, like to say, toilet paper. There might be 20 or 30 layers there, wrapped around that thing. And it's like the cell literally spins around the fiber as it develops and creates that thing. Now, the special area is the node, place that actually generates the action potential, that space between the internode. And that's where the sodium and, no surprise, potassium channels are. This is where the action potential is generated, here. The myelinated part that you see here is a way of shunting current. The potential changes instantaneously down to the next node, where the next one is refreshed and off it goes again. So making these points are not easy to convey. Well, you know, sometimes really good scientists come up with the same results in different places. This is in World War II. I mentioned Huxley. Well, Huxley was busy in World War II. One of the things he was looking at is, okay, how does transmission happen in a myelinated nerve fiber? Well, he actually recorded it. And he did it. Here's a single fiber. There's a node, a node, a node, a node, a node. You see the difference between the node, the successive nodes around 2 millimeters. The action potential is being generated here, 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 and here. And you can see the step. First internode here, onto the next one, onto the next one, onto the next one, onto the next one. Very short time period between, very, very short. So this one might be transmitting at 45, 50 meters per second. Incidentally, Huxley had no idea, but at the same time, Tazaki, investigator in Japan after World War II, I think was published, and at least in an English journal, because of World War II, did similar experiments that showed exactly the same phenomenon. So, and Huxley was very good and generous after the war in attributing to the other guy, Tazaki's contribution here. So that was a classy thing to do, but then he was a classy guy. So what can go wrong here? Well, if you sit on your thumb hard, or, well, let's say lean on your elbow the wrong way. I don't know how many of you have had this happen, but it happens to me. Sometimes you get tingling in these 2 fingers. No other fingers, these 2, because they're supplied by the ulnar nerve behind your elbow. And if you go to sleep that way, and you're leaning against something, and you're not wakened up, and that pressure continues, that nerve may actually be temporarily for days or even for weeks knocked out because of the compression, effects of compression on the nerve. And or ischemia goes along with it. I mean, if you lean on a nerve, you're also squeezing on its microvascular supply, so you're knocking out its blood supply as well as the effects of mechanical pressure. When we come to lower back pain and neck pain and nerve root kind of problems, this is really important. And some people, all of us, can sometimes, unfortunately, develop infections or viruses that provoke antibodies, and those antibodies attack the sodium channels or the potassium channels or both, or the myelin sheath, and destroy them, and can produce acute I don't know whether you've heard the term, but Peripheral Neuropathy. It's fairly common. I used to see several cases a year. Some of them are acute, some of them are chronic. Anyway, we'll get into that in other sessions, but that's what can go wrong. Well, before I hit Oxford, I met this fellow, well, when I got there, I met Ian MacDonald. Ian MacDonald had done this beautiful experiment because no one actually knew what demyelination actually did functionally to nerves. So what he did is he used cats, and he developed an experimental model of demyelination in these cats and compared it to normal. And what he did is something I did actually at one time. Record from the dorsal roots here, being the sensory roots here, stimulated the sural nerve, which is that cutaneous nerve in us down on the foot. But in the cat, he stimulated a little more proximally here. And here's a normal response, a normal delay, nice robust response. But look at what happens in the demyelinated cat. I mean, the delay is kind of 2 to 3 times what it should be, and there's hardly any response. What does that tell you? Transmission is blocked in probably well over 95% of those nerve fibers. And in this case, it was such severe enough, no recovery take place. So Ian MacDonald did a really good job. He was a nice guy. He was a Rhodes Scholar from Australia, another Australian, and quite a job, quite an athlete too. Well, here's elegance, if you want to see elegance of the effect of demyelination. Here we are now. I've introduced, this is a single nerve fiber, which is demyelinated, partly, depending on the node. And it's kind of, and it moved this nerve along a pair of electrodes, that kind of thing. So you see, here's the little electrical signal for one node, and then a little time delay, second node here, the signal gets smaller and smaller, then it jumps again, but a little delay, and then bingo, what happens here? Now we see this long kind of delay at the next node, so something's happening. Demyelination is here, but once it gets going, it keeps going, and then it kind of almost peters out, and manages to get up to here. And another long delay, and then it does what happens in humans. And it almost becomes a squid axon. There is no myelin. Transmission is continuous along the nerve fiber. But you notice what's happening is very, very slow. It's very, very slow. Take away the myelin sheath, and if there is transmission, the transmission is very slow. Now imagine this kind of happening in the brain, in various diseases, tumors, strokes, whatever it is, and happening to a whole variety of nerve fibers and systems. You can see how messages get badly scrambled, both in time and space, right? What the peripheral nervous system can show us experimentally is what we can't show in the living brain, because it's so intrusive and destructive and that kind of thing. But you can see it in the peripheral nervous system. And just take the lessons from a very simple system and apply them to a very complex system. And that's what they're showing here. No, we don't need that. Now here's a patient with acute Guillain-Barré neuropathy. So just to show you here, what we're doing, these are motor nerve fibers. So in other words, go into muscles, and muscles on this side of the hand, sometimes they bung up with biters because of pressure on the lower nerve of the wrist, and get atrophy of these muscles. Anyway, we record for these muscles, and it should be, if everything's working perfectly, and you're recording from those muscles, stimulate the nerve of the wrist, below the elbow, above the elbow, way up in the axilla, and the spinal roots, the signal should look exactly the same, and it does, and normal. But this is the person who developed And the viral infection lasted about 10 days, wasn't all that too bad. And 2 to 3 weeks later, noticed insidious development, a little tingling, but also became clumsy and unsure of her balance, and her strength started to fail. Kind of classical story for Guillain-Barré polyneuropathy or AIDP. Well, this is what she looked like. The signal looks normal, same gain, or almost the same gain here, same muscle group, except that from the, it's already beginning to block across the forearm. This is across the elbow, and by the time we get up to the spinal root, wow, only about 10% of this nerve, of these family of nerve fibers is working. No wonder the person barely moved their muscles in the hand. And the same thing was happening to other muscle groups, the variable intensity. So that's the IDP. That's not uncommon, I would say, back. Let's see, maybe 5 or 10 cases a year. And here's another example where the block was actually uniform, all the way from, this is the foot, recording from the foot muscle here, and stimulating around the ankle, around the popliteal fossa, around the sciatic notch here, and the homosacral roots. And the signal is getting smaller and smaller and smaller. I mean, this signal here, right up by the roots, is about less than 5% of what it is down here. So that's what's happening. And that's the equivalent, is what happens in the central nervous system, say in MS. So we're talking. But sometimes in AIDP, it all functions well enough for most of the nerve, but at a very proximal site, you can see here that this is the axilla, and this is the spinal roots. That's where all of the trouble. Pathologically, that's where pathologists go. Right across the roots and proximal peripheral nervous system. But anyway, so it's not always uniformly distributed. This is a case, I'm not going to walk you through all of this, but just to point out that in chronic inflammatory demyelinating neuropathy, and we probably followed 10 or 15 of these people in Boston and in London, not so much in Hamilton, for years, because they would develop relapses. The extraordinary thing about it was, I remember one man in particular, who, if you walked into this room, you probably might think a little odd, it was maybe a little klutzy, but walking otherwise okay. He's walking with maximum motor conduction velocities of 5 meters per second, where the normal is 50. So it's very slow transmission. And of course, he's lost all his tendon reflexes. Anything that requires synchronization is going to be lost. And so vibration sense. But the other thing that chronic inflammatory demyelinating neuropathy is it isn't limited to the peripheral nervous system. It also strikes the brain, because there's the response for the ventral roots, there's the response to cortical stimulation, very slow transmission in the central nervous system, as well as the peripheral nervous system, in a primary demyelinating disease. And then there's this multifocal conduction block neuropathy. Here's another demyelinating neuropathy, which is really odd. This fellow, I remember, I saw him in Boston. He had no, he couldn't bend his elbow. And the weakness was confined really to the biceps, which has 2 heads. He couldn't do anything. But if we stimulated the nerve very close to where the nerve goes into the muscle, like this, and if we moved up a little bit further, it disappeared. There's the normal response which he had, and the very abnormal response not 100 millimeters away. And but fortunately, very responsive to IVIG and immunoglobulin. mixture, and we're fine. I'll leave that out. But here's a very prosaic example I'm going to return to, because the most common nerve injury in the world is this: carpal tunnel neuropathy. The median nerve gets caught in the carpal tunnel of the wrist. It's extraordinarily common. I can safely say that everyone has it, probably many times, has had symptoms of this. They've often wakened with them. Fingers a little tingly or numb here, and then shake your hands out, and away it goes. And only a few of them actually need surgery. This one did. And look at the tremendous delay. This is one of the things I really gifted with when I was in London, was surgeons who were willing to work with me. And I had 3 neurosurgeons who were fantastic that way, and 2 orthopedic surgeons, 1 ENT surgeon, 1 plastic surgeon. And so I was very comfortable in the OR, scrubbing in and doing my thing, and they were co-authors on studies, and this is one. Yeah.
Oh, there's 2 bits
There
there.
it is. Yeah, thank you. Just put it on there. Anyway, you don't have to know anything else. Just look at these are 20 millimeter differences between here and here and here and here. Look at the huge delay and reduction in size. So this would be about 20 internodes in length. It probably didn't affect all 20. It probably affected 5 or 10 of them. But it only needs to affect 5 or 10 to cause that and the permanent symptoms. Now you say, well, gee, when I was learning to fly at the London Flying Club, there was a lady behind the desk. She was the secretary on the flying club, and she happened to be a patient of mine at one time, and she had a carpal tunnel neuropathy, and so I sent her off to another surgeon, and didn't hear anything back from her or from him. But she was behind the desk, and I looked at, she put out her hand, and I looked at her, and all the muscles supplied by the median nerve were gone, were atrophied. He had cut the nerve in 2 by mistake. Easy enough to do, but he had. And I said, gee, does that bother you? No, I'm really grateful to Dr. So-and-so because the tingling and all that, but you know, Dr. Brown, I still have that numbness. I can't feel it there. And I had to point out the waist chart, but she hadn't noticed that. And so I got a hold of the surgeon, and I said, I don't know, but I think you transected the nerve. And actually, it's a perfect case to do, to repair, because when the nerve regenerates, it doesn't have to go very far. It doesn't have to go from here to there. It only has to go from here to there. And so he went back in, and I was just an observer. They obviously can't align thousands and thousands of nerve fibers perfectly. They often think that beyond anyone. But alignment as he did, stitched it up, and lo and behold, a year later, the muscles were coming back and the numbness was going away. And she wasn't, to her it was, she was just glad that she didn't have all that pain that she had before, the burning kind of stuff before, and she was, anyway, so a good outcome from it. Have any of you know anyone who's had Bell's palsy? Facial palsy? Well, it's common enough in our age group, I'll tell you. So what happens is that somebody is often mistaken for a stroke. And it affected my cleaning lady one time, several months ago, and she came around and I said, I think something's happened here, and the facial muscles, frown, pull up here, close your eye, pull hair back. It supplies all the muscles on the side of the face. And if the nerve is affected, well, then you get, number one, the big thing that happens, the big risk is that people can't close their eye properly, so the cornea is exposed at night, which is a very dangerous thing to happen. So we have to put an eye cover on overnight. But anyway, this is a person with exactly that. And actually had a good prognosis because the size of her nerve response beyond this trouble happens, by the way, in the base of the skull, not on the side here. It happens in the passage of the nerve through the skull. And if you happen to operate on them, as some surgeons do, and take the roof off, you often find the nerve is just jammed in that small hole. Normally there's enough room, but in this case not. So the nerve actually is in trouble because the blood supply is cut off, as well as the pressure. And but the response is very much smaller, proximal to that canal than it was beyond it. So that was, and that one recovered very nicely. I'm not going to go through this because I want to talk about this kind of thing. Nerve fibers anywhere. If something happens to them in Alzheimer's disease or motor neuron disease, you name the disease, nerve fibers die back from their terminations. After all, if you have a nerve fiber in the lumbosacral cord and a muscle down in your foot, that's a lot of nerve for the cell body to support. Where most of the metabolism, making of proteins takes place, they all have to be transported to the end. So guess who's on the end of the tether? Those parts of that nerve fiber that are farthest away from mother, the cell body. So nerve fibers, so if somebody comes in and says, I have tingling and numbness in my feet, and then a few months later, it's up to their knees, it's not surprising for the fingers to be tingling by now, because now you have an equivalent length. Follow what I'm saying? You know? And then as it advances up to the thigh, and it's up to the elbow, then they get a little numbness in the ventral abdomen because the fibers are coming out this way. So it's a length-dependent nerve lesion or single cell disease in all of the neurodegenerative diseases that affect the central nervous system and the peripheral nervous system. Same kind of thing, except we can actually see this. And it's very easy to recognize the pattern. It doesn't matter what the cause is, whether you're diabetic or some toxin or nutritional deficiency, you name the cause. The pathophysiology and the pathology is the same. So that's the principle that I'm after here. And this happens with my good friend down in Homeless in Hamilton. Studied a lot of cases of ALS, and we've certainly had our experience of that here in Niagara Lake. And this is the rate of loss. Now this is only a year and a half on this scale, and there's 100%. You can see the steep fall and the loss of nerve cells. But if you pay attention here, or look, this is the control group, but the control group is not normal. People in our age group are losing motor neurons at maybe 1 a month, something like that, if you do the numbers. And which means that there are 10 more that are a little sick that haven't died yet. You see what I'm getting at? Because I can come up with innumerable examples of this kind of thing, different diseases, that kind of thing. But what I'm getting at here with the skipping some of these other slides. Doesn't matter. It's something I wrote a little article for, so it's not in the papers, but when is a disease aging? You know, physicians for centuries have thought about, as far as health goes, and as diseases. You had the bubonic plague or whatever, really bad things, infectious diseases. Sure enough, those are COVID. But even if you take COVID, who were the ones that ended up in hospital or died from COVID? They weren't people in their 30s and 40s. Now, they were in the acute thing, or the very early stages in New York City, but that was a reflection of the intensity of the contact of care workers, physicians, nurses, other staff, every day being exposed multiple times. So the point is, and we did a series, I did a series last year, and I would suggest, not because I did it, but because the information that was based on that series on aging last September. It ran for 4 or 5 weeks. It's on YouTube. And the library has, you can look it up. That's a good series because the key figure that drove my reading and my perception was the Nobel Prize winner on protein stuff, and they certainly do his business. Aging is full of crap. And even the New York Times, you look up their health kind of stuff, they never know what to do. But this hard stuff being based on the same kind of hard evidence that Hollister and Huxley applied to their stuff. And it's a good series, not because of me, but because of the content. So you might want to look it up. But I'm struck having three things, preparing for this, having done a series on AI, and also a series on aging. I'm struck with the connections between the three. And we can talk about the AI kind of stuff a little later, but certainly on the health side, listen, as we get older, almost every animal that's been studied, cells die. And they do, and they begin dying somewhere in the midlife. And what do I mean by that? Cells are incredibly complex. They have multiple systems, not just chromosomes and genes, but a whole lot of other systems that are there to create all the thousands of proteins that we need, and the various organelles, functioning tissues in the cells. And little by little, those subsystems in the cell start to fail. Not kill the cell, but the cell's not working quite as well as it might have. Now, if you are unfortunate enough to be in certain parts of the world and deprived of proper eating and that kind of stuff, you're going to fail a lot faster. But on the assumption of that you're doing your best, no one in this room is going to reach 120 with everything intact. In fact, I venture, looking around the room, including myself, none of us here are what we were 20 or 30 years ago. Well, we socialize with people in our group, so it doesn't look like much because we're all in the same basket, right? In various forms. You say, oh, so-and-so looks really good, or look at this. But the fact of the matter is we're all kind of on this same trip. And I'm not depressed by this. I'm trying to make a point about healthcare. And if that cellular failure happens to affect certain proteins, you will get, or the risk of Alzheimer's and various other degenerative dementias is going to increase. But it would be a mistake to think, look, they provided updated numbers just recently on the prevalence of dementia. And the numbers are really scary. I mean, I'm in my 80s, so somewhere between 30 and 50% of people in my decade will or have developed clinical dementia. Meaning, if you did the test, yeah, and we could argue about that, but and 80% in their 90s. With numbers like that, that's not a disease. That's aging. Because it affects everyone. And it changes your perspective on if you were trying to do something about this, how you would go about doing it. Because what tends to happen in the way things are is you get the huge mistakes happening recently in the treatment of Alzheimer's disease because of these monoclonal antibodies developed by different pharmaceutical companies in various shapes and forms to kind of get rid of beta amyloid and tau. And it all kind of makes a certain sense. But you know, they're not very impressive for what they do. If you look at the pictures, they're really good. Meaning, do they get rid of it amyloid? They do. Are the patients, have you stopped the decline, the cognitive decline? Absolutely not. Have you slowed it by much? Not by much. And what makes all of this worse is the scandal that surrounds us. I mean, a huge scandal now of the lives and misrepresentation of stuff, and the whole Alzheimer's kind of world, which I wasn't fully aware of until a few months ago. I'm certainly aware of the tension between pharmaceutical companies and the FDA in the United States, the approval agencies. But to return to the point, the drugs, and there are 10 of them at least now, are not very effective. There are many people who think that the hypothesis is wrong. I happen to be one of them that believes that. They're barking at the wrong tree. But they have a huge investment in stockholders and everyone else. They've invested billions of dollars in this, that, and the other thing to see that they're approved. So, but the point, if you change the orientation to aging, then you're not left trying to manage every kind of manifestation of that, which we label as a specific disease, and you really are going after the fundamental underlying cause of what's actually going on. And now today, I'm going to shut up in 2 seconds, but today we're talking about signals in the nervous system. Well, from the literature I'm aware of, my own experience, that's yet another manifestation of this scrambling with aging. Messages getting scrambled. Difficulties in memory and learning, which are reflections of protein disorders, and lipoprotein disorders because of mutations, and so faulty proteins are forming. Surely it makes sense to step back and to have a wider perspective than go after that. I don't think that's probably going to happen anytime soon. So I wanted to set, this wasn't my intention to start out with this stuff, but when I got into the stuff about the peripheral nervous system, I realized this was a window into the central nervous system. And also in the background, I've been very aware about all this stuff happening with Alzheimer's disease and the other dementias, and because of that aging series, I learned a ton of that stuff. So if you're interested, you might have a look. So, any thoughts? We can't all agree. This is just went to the hospital for a week. Any questions?
No, I can just comment on what resonated with me, because I had a terrible motor vehicle accident a few years ago and broke many ribs, had laceration, lots of bones. But in healing, you know, I definitely resonated with me. There were certain functions that I was worried wouldn't come back, but they did, and I do feel that the neurons can be regenerated, restimulated, whatever. And now I'm dealing with a bunch of stuff, and something resonated because I've been getting all these, you know, numbness down the leg and whatever, and now I'm having gastral issues. So, and I feel like what you said with regards to, you know, the stage of where the nervous system is, and that now it's reaching out further, resonates with me. But who do you talk to about that? I mean, who do you, like, right now the doctors have me dealing with, you know, pain medication to deal with some of the stuff to sort of dull the nerves, right? But that can't, I just feel like can't be a solution. Like, I feel like that can't be a way to, it's almost like, well, you have this, whatever is going on, you can't quite pinpoint it all, but just take these and you'll be fine. And so, I mean, do you have any recommendations on, I don't know, specialist or doctor or someone that might be more helpful to me?
One of the problems in healthcare professions of the last 20 or 30 years is that they become more and more smaller field.
Yes.
And yes, they know a lot more about that smaller field, but even worse, they're not interested in anything outside of that field. And it's happened with science too, because people tend to focus on what the last place that they were and take the next step, but there aren't many people who it's very difficult because it's hard to find. This is probably why there was another series we go out there that and it was alternative medicine, meditation, that kind of stuff. And the reason why I took that on was because I knew almost nothing about it, and I knew that most of my colleagues were much better. So I mentioned this before, if you ever want to learn something, teach it. Teach yourself first, and in doing that, and teaching, sharing that with others, you learn a lot. Mm-hmm. And that's also a worthwhile series to look at, because one of the great strengths of that meditative focus is that it's much broader. Mm-hmm. And for example, Harvard, believe it or not, maybe 10 or 15 years ago, was one of those very incredibly successful institutions, and almost each physician had a disease. And then they realized that their patients were coming in and they weren't getting their questions answered, and they weren't happy with the experience, and they weren't being listened to. Which incidentally, when AI came into Harvard, one of the things that the patients liked was that AI listened. And actually helped. Have you tried it in a way?
Yes.
With ChatGPT, the latest version.
It does actually, it's scary gives you good.
It is, but anyway, I'm not suggesting that as a thing, but the point is that why were so many patients unhappy? Because they didn't feel that they were heard or understood. And part of that was because if you see a plastic surgeon and the only nerve they operate on is one or two nerves, and that's what they do, they're not going to be very helpful to unless you have that nerve problem. And I think it's a real hole in healthcare. I mean, I know that doesn't sound very helpful to you, but at least 20 or 30 years ago, but physicians have a lot to answer for that, but there were many who were not that listened. And listening is actually very helpful because you're learning from the person you're talking to. Yeah. And your experience problems, if you're always in this tone of what you do in the OR, or particular toy that you play with, you're not going to learn much from it. So, now you got me thinking that would be worth talking to. No, it is, because
I started seeing internal medicine doctor, Gruber, he's in St. Catharines.
Yeah.
We'll see. I mean, nothing makes sense, so.
Broadly speaking, there are very good family physicians. But, broadly speaking, my experience from the American system is that internists were much better at handling things because they're actually properly trained in this. And they had 4 years after graduation, and versus say 1.5.
Right.
2, yes.
Hi, I was hoping that we would be getting like a 100,000-foot view of neurology in some ways, because I think that it's still the Wild West. I think there's just so much that is unknown that, you know, this whole thing about cause, like what causes a neurological disorder. Is it environmental or is it genetic? And then what happens is the symptom of a neurological disorder is pain, or it's it's immobility, or it's something that happens. And so I think we haven't really gotten back to root cause on some of this. And then there's also the number of wacko.
Lecture 1.
Which one?
Lecture 1.
Yeah, well, wacko diseases, there's so many different types of neurological disorders. There seem to be, like it used to be cancer was, you have breast cancer or prostate cancer or lung, and now it's all kind of cancer. And we have drugs and chemotherapy and we have surgery. Whereas with neurological disorders, it just seems that there's not a lot of answers in the way that people want them.
Yeah.
Like, in other words, you're kind of saying, well, yeah, you've got pain. Well, okay, I can treat the pain in this way. What's causing the pain? Well, we know that, the nerve's degenerating here. Like, it just seems like we're still at a very early stage of finding a lot of answers for these things. It just...
Well, it has certainly changed, becoming far more complex, say, in cancer. Let's just speak to that. And anyone needs to go. See you next week. Anyway, on the cancer front, it's both encouraging and discouraging. Encouraging in that with glioblastoma multiforme, which was the most terrible of brain cancers, with a 5-year mortality rate of well over 50%, no matter what you do. And esophageal CA is far off now. Well, for a long, long time, these things were treated as a surgical problem. Take out the tumor as much as you can, and or even this will sound awful, but neurosurgeons use the term in the coffee room: debulk the tumor. What do they mean by that? Take out as much mass as you can, so there's less pressure, because the pressure can cause troubles. But now we realize that to return to the story of the esophageal CA and the glioblastoma multiforme and later stages of breast cancer, it is true that certain mutations are really important, say, in breast cancer. Right? If you have the BRCA2 gene, the risk of ovarian cancer, breast cancer is way off the chart, and for prostrated males. very, very aggressive cancers. But that's only the beginning. Because once the cancers are there, cells are, when they're birthed, when they're differentiated, when they form, they're good citizens. They work together in their local community well. They identify with one another. There's no destructive behavior. They're very cooperative with one another, and they recognize one another at a molecular level. But when they mutate past some of these barriers. And what happens when you, for example, with glioblastoma multiforme, or say secondaries in the brain from breast cancer, and did a genomic map of just different regions in the cancer? Well, they're quite different. So the genomic sequence, if you map it all in area A, is not the same as it is in area B. It's the same as it is in area D or that. I mention that because some chemotherapeutic drugs or immunotherapies are, particularly the immunotherapies, are specifically tailored for specific genetic abnormalities. And if the cancer's already going to end run around that, or doesn't end run around it, it's no longer effective. And that's one of the real problems now of trying to keep up. I call it evolution on the fast track in a bad sense, meaning stuff is literally happening on the run. And you can actually see this in sheets of cells that are spread out on an agar or large agar plate. And yeah,
Sorry, I'm sorry.
yeah, that's okay. And with the appearance of certain new mutations, all of a sudden those cells are, it's like the Boston Marathon, and the last 2 miles, suddenly you've got all your energy back, you can run like crazy, and nothing's holding you back. So cancers are very, at the cellular level, very opportunistic and genetic. That's what we're learning. But imagine, too, how incredibly expensive it is to track this kind of thing. How is somebody going to sample a cancer? They can't sample it everywhere. Choose someplace. That's like in the prostate cancer, when men are being followed, I think it's 8 or 10 sites that they do sample. But it's exactly that, it's a sample. It doesn't necessarily reflect, well, the prostate, and maybe not the part of the prostate that's going to ultimately kill that person.
Well, I don't mean to get into a discussion of cancer. I just said that with neurology, it just seems to me that there's still an awful lot of things that are being figured out.
Oh, absolutely.
And so I don't know, I mean, I've been living with, my husband has a neurological condition for years now, a degenerative neurological condition, that there's really there's very few treatments that work. There's very few, it's just a slow degenerative process. And so you have to go to more holistic health, like diet and exercise and, meditation, or, I mean, it's kind of like there's, I think it's still the Wild West frontier of what do you do, like, even how, why a neurological condition happens, like, is it environmental, is it genetic? Like, yes, there's testing now you can do for different types of neurological disorders, I guess. But I'm just saying, it seems to me it's kind of still a very new frontier. And there's probably nothing worse than being in debilitating pain, for people that suffer with, the painful kind of neurological conditions. Then there's the motor neurological, and then there's the autonomous neurological. Like, I think there's still a lot of stuff that seem to be figuring out here.
Oh, there is.
And so I think it's encouraging to hear that, but when we're living with this, a lot of people are suffering, I think that Miguel was saying.
I agree.
So that was what I was wondering about the 50,000 or the 100,000 foot level. Like, I hear more and more about brain studies that are being done at Sunnybrook, at the Ontario Brain Institute. So I think it's good that there's more and more research going on. But whether it's landing at therapeutic end of things yet, in terms of what helps you deal with degenerative neurological condition. Like that chart you showed with ALS is pretty scary to see the progression that can happen so rapidly. You know, just what can you do about that? I mean, we're used to solutions, and I guess there's not a lot of solutions I see happening in this field of medicine.
Not on neurodegenerative disease, that's for sure.
Yeah.
Better with diseases like MS, where some of the treatments have certainly got a lot better than I remember 10 years ago. And so the prognosis is better, the outcome. But they don't stop the disease, they slow it. And I mean, it's incredibly difficult, and part of the problem is you can invest a lot of money in, you know, there are 4 or 5 of the best medical journals in the world. One of them is the New England Journal of Medicine. It has literally become a journal of clinical studies, clinical trials. And, you know, these are trials that, for the most part, take 3 to 5 years to do. In the case of Alzheimer's disease, might cost the company half to $1 billion, $200,000 at least per patient, per subject, and the studies, so they're incredibly expensive to carry out. And they all assume they have a working hypothesis and for it, and for many years it was the amyloid hypothesis. I think the amyloid hypothesis is probably wrong as the primary agent. And there are increasingly more people thinking that, but the problem is that you have large institutes heavily invested with one hypothesis that they're clinging to like crazy. And it's very difficult to change the mindset because so much is invested in it. Whole careers are invested in this kind of stuff. If you spend the last 25 years of your working on the amyloid hypothesis, you're going to be pretty, or feel that your work and career was a failure. If somebody comes along and says, well, it doesn't work out. This kind of control in medicine, dictated by clinical trials, I'm not against clinical trials, but their expense and their way of controlling investment in medicine and controlling research is taking us down a dangerous route, because what if the working hypothesis is wrong? How do you get out of that rabbit hole when so many people are invested with that idea? So it's a real problem in medicine. Healthcare is very expensive, especially south of the border. But clinical one of the things that I will say in general in science, and then Nobel brings us back every year. I mean, there are 3 science prizes, one in physics, one in chemistry, and one in medicine or physiology. The least creative of the Nobel prizes is the one in medicine and physiology. Not always. That stuff on the sensory receptors that I showed you there, that was a really elegant piece of work. And that was a medicine prize. And so they do some really good things. But some of them are, particularly in cancer, you know, it's kind of the drug of the decade. And they're kind of focusing on it. It's too much money going down a single path, and it doesn't reflect the patient experience of their illness, because it's one thing to have a particular kind of cancer, but that person is a is first of all a person and living a life, and has all kinds of influences on life, living, and those things matter, but no one's listening. One of the things that encouraged me, though, was a friend who had gone down to the, when I was doing a part-time thing at the time of day, I had access to the Mayo Clinic. And I've long had colleagues and friends work there. In fact, one of them was the CEO of the place. But one of the patients said, you know, you go down there, it's really quite an interesting experience, but the first hour or hour and a half is actually spent, we're not here to talk about your symptoms right now, we want to find out about you, who you are, and what's going on in your life and that kind of thing. And then we'll get to the other stuff, and they do, very step by step. And the other great asset they have is communication, because if you see Dr. A, and you go to see Dr. B immediately sees what Dr. A said or thought. So he doesn't have to wait to read emails or anything else, or wait for the mail to arrive, that kind of thing. So, and then at the end of the day, there's a conference usually. And if you're down there for 2 or 3 days, a conference at the end of the things. And then sometimes I was at the receiving end. I'd no sooner get back to Niagara Lake than I get a phone call from Mayo, from whoever I said it to them, and her. And they would kind of bring me up to date on what they're thinking about. That's the way the system should work, I think. But understand that Mayo is very expensive.
There's certainly no Mayo Clinic in Canada. I think that's
Well,
what there is. It's not.
they have a presence. They almost came here, I don't know, 10 years ago, no more than that. And what happened when the fellow I knew was the CEO, and they were really thinking about moving to Toronto, they were inundated with Canadian physicians who wanted to jump from wherever they were at Toronto to join the new Mayo organization. And why? Well, not because they were going to be paid more. In many cases, they were going to be paid less. But because of the quality of the team and the way the clinic operated. I mean, people don't leave Mayo. I mean, they like to work there. And because the place has a team spirit about it. And it starts at the top. It's a very interesting place to be. The Lay Clinic is a kind of a small version of that, and Boston. I think the Cleveland Clinic is really fairly close. I don't know the Cleveland Clinic as well, but organizations like that have a broader view and have more people on board that can cover different nuances of things can be very helpful. The trouble is, it costs money. Now, some of these things are U.S. being what the U.S. is. This stuff is covered by a company or if you're in the military, sometimes the military, that kind of thing. And but not the general public. I think our system overall does a better job overall. Because the American system, there's so many people that don't support it. And there aren't as many, nearly as many that fall so completely through the cracks on this side of the border compared to that side of the border. So that's what I think. Okay. That's a very interesting perspective. Very interesting.